feels like there's not a lot of people here.
Okay. Well, the important people are here.
I agree.
Okay. So Unit 3 is about bonding between atoms. Now, some of this is going to be about what's going on inside atoms that allows that to happen. So in Unit 2, we spent a lot of time looking at orbital notation, electron configurations, and sort of wrapped up at the end with, not at the very end, but near the end with electron dot notation. Okay, and all that's going to be used as we discuss the theory behind bonding and how it happens. So let's start with a really simple molecule that you guys are aware of. Huh? Now, hydrogen is a nonmetal. When we were looking at regions of the periodic table in the last unit, we figured out where the metals and nonmetals are. And where are the metals? Yeah, well, it is the middle, but it's not just the middle. It's everything from this stair step over here. All this stuff are metals, except hydrogen doesn't belong here. When we were showing the regions of the periodic table, we said when we look at what are metals and nonmetals, hydrogen needs to be moved where? Where? To the right. Next to helium, right there. Okay. In fact, some of the periodic tables in here actually show it sitting right there. Okay. All right. So when we're talking about metals and nonmetals, hydrogen is not considered a metal, so it's going to be over here. Okay. So everything from here this way is nonmetals, and most of the stuff that's right along this stair step, what do you call those? Metalloids. Okay. The noble gases are this last column. All right. So this is made of what kind of atoms then in those terms? If it's water, you're fine. Just make sure you put it in your book bag. Okay? What's over here? What's over here? Where does hydrogen belong? What kind of atoms do we have? All the nonmetals. When you bond, now you should know this in physical science, except for the one person who doesn't take physical science, who incessantly reminds everybody of that. And we're joking. Okay, you can't see me smile on the video, but all right. So we have all nonmetals here. And in physical science, you learn what kind of bonding you have when you have two nonmetals bonding together. What kind of bonding is that? Two nonmetals always bond covalently. I'm not going to reteach stuff from physical science. I'm going to remind you, but your responsibility is to write it down and remember it. Okay? We're not going to practice this because it's something you should have learned. I'm sorry about that. You're going to have to learn it, this way. All right? You have to learn. Okay? You were taught it in physical science. This is just a reminder. Okay? All right. No classroom practice on what's a metal and a nonmetal and what kind of bonding you get. When you bond a metal and a nonmetal, what kind of bonding do you get? Say it again. Ionic. Okay? There's your reminder. All right. So this is covalent bonding we're talking about here. Because it's nonmetals. All nonmetals create covalent bonds. And that's not always true. There are a lot of exceptions to that. But in general, you can kind of make a pretty good prediction that you have covalent bonding when you have nonmetals bonding together. And you have ionic bonding when you're putting metals and nonmetals together. Okay? So if we have covalent bonding, what happens with electrons when you do covalent bonding? They share. Okay, in covalent bonding, there is sharing of electrons. Again, that's physical science. I'm not going to spend a lot of time reviewing that. Well, if we put this together, if we looked at what we did in the last unit at our orbital notation, that's the orbital notation for hydrogen, and we've got two of those. Yep. Oh, I don't know why I put the bottom on that. That's supposed to be an arrow, two arrows. And then oxygen you should be able to do this with me. If you don't have out your periodic table, you should have had it out a long time ago. You're going to need your periodic table from now on and forevermore. Almost every day. Not every day, but close to it. And you should be able to do this without me having to go through it and show you how and remind you. Okay, this is going to be really important. All right. So what these orbital notations show you are how the electrons are arranged in orbitals. Now, it doesn't show you the three-dimensional physical shape. It just shows you where they are in orbitals. Okay? So, what an atom wants to do is to have a full valence level of electrons. That's what atoms tend to want to do. They want to have a full valence level of electrons. So how many more electrons will this hydrogen want to have a full valence level? One more, because it only has one. It's only in the first primary level, the first primary energy level 1 here, and you know that because hydrogen is in the first row of the periodic table. Okay, and hydrogen is in the S sublevel region. We're talking about sublevel regions. We move helium back over this way. So S sublevels are here. S sublevels is all there is. And S sublevel is all there is in that first primary level for hydrogen. And then you can have a maximum of 2 electrons in an orbital. Okay? So it wants to share electrons such that there's another electron right here. Okay? How many more electrons does oxygen want to have a full valence level? 2. So somehow or other, we've got to get these 2 hydrogens sharing with this oxygen. Okay? Now we could do that. It gets a little bit complex, but one of the points behind orbital notation is that you can see where the electrons are coming from. Okay? Eventually when you get to more complex molecules, it's so complex you can't even see it anymore. So we're going to take, and I'm going to redraw this in a way that overlaps this orbital with this orbital. Okay? Now, in reality, that's what happens. Orbitals actually overlap. They merge together and become one. Okay? That's how you get sharing of electrons, and we call that covalent bonding. There's actually a sharing of the orbital itself. Not just sharing the electrons, but sharing the orbital. So if I write out oxygen in this manner, the orbital notation for oxygen, here's 1s. And I'm going to write out 2p kind of strange looking, okay? I'm going to do this one like this. And I'm only going to do half the box here. And half the box here. Because I want to show hydrogen kind of overlapping those. And I'm going to use hydrogen in red, okay? So I'm going to kind of turn hydrogen sort of sideways. I'm going to twist its orbital notation around a bit. So that instead of putting the hydrogen symbol to the side, I'm putting the hydrogen symbol above. Okay? And instead of putting the 1s, well, actually I should have left more room. I should have left some room for 1s here. Let's do it that way. And instead of putting 1s underneath, I'm putting it on the top. Okay? And then I'm going to complete the orbital to show that it's sharing by doing that. Does that make sense what I'm doing? Okay? And so here, I'll make it a little bit better. I'll put a colon there and the 1s here, and show how we're overlapping in that manner. Okay? Now both the hydrogens have a full valence level, and the oxygen has a full valence level too. And that's one way to think about it. Unfortunately, it isn't quite correct. Okay? And there's a lot of these are called models. These are ways of thinking about how things happen that you can't see. We talked about that a lot in Unit 1. Models are ways that scientists think about things to help explain how it happens that, in this case, bonding occurs. Okay? Well, there's some other things that happen. Remember our orbital notation? Our actual orbital drawings? We said that an s orbital was spherical, so these orbitals here are spherical. Right? See that little model up here? There's an s orbital with the 3p orbitals inside of it. So this is not the first primary level. This would show at least the second primary level or higher. Okay? So the second primary level then has 3p orbitals. One that goes this way, one that goes this way, one that comes out in front and kind of back behind, and then the s orbitals around it. All right, that makes sense? Remember all that? And so the 2s here is this part right here, and this P might be this double set of balloons here, both sides. This P might be this set of balloons, top and bottom, and this P might be that one, top and bottom. Okay, so we really have to include all of that. All right. What we know about when oxygen and hydrogen bond is they don't actually take up this shape that this would imply. If I were overlapping a p orbital here, as I did here, with an s orbital from hydrogen, and that's what we're showing here, and I were overlapping a p orbital here from oxygen with an s orbital from hydrogen, the oxygen molecule shape would be at 90 degrees to each other. No matter where you put that hydrogen, each hydrogen will be 90 degrees from one to the next. Does that make sense? Okay? That's what it would be if that's the way the bonding occurs, like this. Okay? That's not what happens. Okay? So what happens is something called hybridization. At least that's the way, theoretically, scientists think about it. Hybridization. You ever heard of hybridization or hybrids? Where have you heard the term hybrid before? Like cars. So what's a hybrid car do that's different from a regular car? It's both gas and electric. So it's not just a completely electric car, not a completely gas-powered car. It's a little bit of both. Okay? Well, hybridization means these orbitals I had up here, they're not completely s orbitals and not completely p orbitals. They're somewhere in between. Okay? Hybridization means we reform s and p orbitals into new kinds of orbitals that are in between. Now those round balloons you had for the last lab we did, we're going to need another set of round balloons for another lab we're going to do on hybridization. Okay? And you're going to need a set of long balloons. Okay? Huh? We're going to need a set of round balloons and long balloons. The same place you get the round balloons. I hope. It's just long, like the kind you make those balloon animals out of. So, buy a pump. Okay? If it's so hard to blow up, get a pump. Or buy the really inexpensive ones, the ones that are hard to blow up. So, you get what you pay for, right? Alright, so you're going to need, for that lab, that's just kind of an addition, upcoming lab, need balloons, round and long. Okay? When? When do you want to do it?
Tomorrow.
Yeah, you can do it tomorrow. Sure. I've got the videos on the website already. Sure. It's on my YouTube channel.
Can we do it Thursday? Wait, when's the test?
Yes, it's Tuesday. Okay. By Wednesday, we need the balloons. Okay? By Wednesday. We'll do that. We'll do our modeling of hybrid orbitals and things like that. We'll start that on Wednesday. Okay? By Wednesday, when you come into class, you've got to have a package of each. Okay? Now, if you have a handful of balloons, you didn't buy a package. Okay? You just got somebody to share some with you. I can't give you credit for it if you don't have a small package of those kind of balloons. All right? Got it? All right. Yep. You still have it in the package? You're good then. Okay? As long as you still have the package that's open and with the other ones in there, that's okay. I don't expect you to buy balloons you don't need. Now, you're going to need a number of those balloons, those round balloons. So I don't know how many you're going to need, really. That's why I said package. Okay? So if you run out, you may have to go buy some more for the next time we do it. We will be doing it over several days. Okay, a little bit here, a little bit there. All right. So what does that mean? Well, here's what we know about the bonding between oxygen and hydrogen. They don't form this 90-degree angle. Okay. Okay. The real angle between hydrogen and oxygen is 109.5 degrees. How in the world do we get that? Well, if you compare that with some other molecules, like, for instance, ammonia, the angle between all those bonds is also close to 109.5 degrees. It's not exactly 109.5 degrees, but it's pretty close. Or methane. So this is ammonia. This is water. And this is methane. And when we solidify these, when we take water and turn it into ice, when we take ammonia and turn it into solid ammonia, we take methane and freeze it, and it's hard to do that. It has to be really, really cold to do that. But we start seeing how they stick together one to the next. And it helps us, among other ways, to figure out what the actual shape of the molecule is. Okay? All of these have bond angles that are roughly 109.5 degrees. Now, water is actually a little bit closer than that, and so is methane, so is ammonia, but methane is pretty much 109.5 degrees. So, people that are way smarter than me have looked at these molecules and a whole bunch of more complex molecules and figured out why this might happen. And that's where they come up with this thing called hybridization. Okay? Well, here's what's really going on, according to the theory. So let's take oxygen, and let's look at its orbital notation. 1s, 2s, 2p. So what really happens is, or what the theory is, the hybridization theory is, that all of these orbitals, the s orbitals and the p orbitals, merge together and form a different kind of set of 4 orbitals. Still 4 orbitals, but they're not s and p orbitals anymore. They're called sp. Actually, these would be sp3s, because there are 3 p's and 1 s. 1, 2, 3, 1s, 3 p's, sp3. Okay? So what they do is they hybridize and you get that's 2 sp3s. Okay? Now the 3 here is not the same 3 that we use in electron configurations, okay? If I had a P3, like 2p3, if I were writing electron configurations, that would mean I had 3 electrons in the p sublevel, right? Okay, but that's not the same 3 here. This is a different 3. This is sp3. It's the name of this new kind of orbital that's somewhere in between. And instead of having one s orbital in that second primary level, we're talking about the second primary level here, okay, s and p are sublevels, so sp3 is a sublevel. Instead of having this s orbital and the 3p, I should have made this a different shape, but that's okay. Instead of having all of that, what happens is this s takes a new shape, all the p's take a new shape, into single balloon shapes. So our S becomes this, and it's not S anymore, it's sp3. Okay? And the P's become this same thing. All the same sort of stuff. And so all of these are sp3 orbitals. So that's just like 4 round balloons, isn't it? Does that make sense? Because there's one S and 1, 2, 3 P's. Remember our balloon shapes? Right? One S. In our model up here, above the screen, the 2 green balloons that make up a p orbital, 2 yellow balloons make up a p orbital, and the 2 orange balloons make up a p orbital. Over there, I've got a similar set of p orbitals. It doesn't show the S. Okay? But they're all going to reform themselves into 4 orbitals in the same sublevel, and the only way to get them all together is like this, because they're all the same energy and they're all the same shape. And so they form what's called a tetrahedral. Okay, they form themselves in a tetrahedral arrangement. So what that means is if I take a really long, straight needle and put it right through the middle of a balloon, so here's a balloon, I'm going to put a needle right through the middle of it like that. That's the axis for that balloon. Okay? Like an axle on a wheel, right? Well, the axis is the middle of everything. In biology, you looked at axes when you're talking about whether things are symmetrical, right? Okay? And you had to figure out where the axis is down the middle of it, all right? Well, we're looking at an axis through this balloon, and an axis through this balloon, and an axis through this balloon, and an axis through that one. And so what you get is, here's one axis, here's another axis, an axis that's going to come out away from the screen toward you, and one that's going to go back behind the screen away from the paper. And all of these are at 109.5 degrees apart. Well, now we're talking in 3 dimensions. Okay? It's no longer a 2-dimensional idea. It's a 3-dimensional idea. The triangle is the angle coming out toward you. So it's like I have an angle not flat on the paper like this, but swinging up toward you like that at 109.5 degrees from both these 2 angles. That make sense? What? Okay, so if this is 109.5 degrees here, which is less than 120, more than 90, I have it like this, and I swing one of them up toward you. See what we're doing? So you get them like kind of like that, and that's kind of that's hard to draw on a two-dimensional sheet of paper. Okay, we'll do that after class. Okay. Yeah, I've got a gift for you here. All right, are you with me so far?
Yeah.
All right. So, the reforming of the orbitals from S and P into these hybrid orbitals called sp3s force them to arrange themselves in this sort of arrangement. And that means that if I have this oxygen atom in the center, and I've got one orbital coming up like this, another orbital coming out at 109.5 degrees, one coming toward you like this, and one back behind, all right? Then the s orbital from the hydrogen, remember the s orbital from the hydrogen is just a spherical shape, okay? So they just attach themselves on here. Hydrogen's kind of there, all right? Makes more sense with a 3D model. That's what we're going to do. That's what we're doing with the balloons on Wednesday. Tetra. This part means 4. Hedral just describes a 3-dimensional shape. 4 and 4 things. 4 corners. Actually, it's 4 corners. A tetrahedron is a 4-sided shape that has 4 corners. or four, corners, I guess, yeah. Huh? Well, a square has 6 sides and 8 corners. A tetrahedral has just 4 corners. It looks like kind of like this. There's a tetrahedron.
So it's a pyramid.
It's kind of a 3-sided pyramid. Not a 4-sided pyramid, but a 3-sided pyramid. Okay, so this is a tetrahedron. Whoops. All right. So if you think of the nucleus of this oxygen being right dead in the center of this tetrahedron, then each of these right here, the tip of each of those would go right at the corners.
Does the one on the bottom left have a hydrogen too?
No, there's only 2 hydrogens in oxygen, right? All right, so let's go back up here and look. I have 2 orbitals that already have a full set of electrons, right?
Yeah.
So they're not going to bond with anything. Okay? These are here. There's 2 electrons in here. In those orbitals. And these hydrogens, if we did what we did before, let me do that down here, with the overlapping orbitals. I'm going to do 2 sp3s. And so 2 of those orbitals already have a full set of electrons. But we're going to do 2 of them that we're going to overlap with hydrogen. So we've got 1 electron from the oxygen and 1 electron from the hydrogen. Okay, overlapping that. All right, so that's what we have here. And so we've got 1 electron from the oxygen in this shared orbital now. We've got also 1 electron from the hydrogen. Does that make sense? All right. Now, when I get to really complex molecules, this becomes so cumbersome as to be useless. Make sense? Imagine doing, I don't know, let's see. What if I did methane that way, where I've got 1 carbon and 4 hydrogens? After a while, or let's look at this. Suppose I did carbon tetrachloride. So here's carbon tetrachloride. All right, and a carbon atom has this orbital notation. Let me show the hybridization of carbon. It's going to be 2 sp3 here. Yep. So there's carbon in its hybridized form. Okay. Here's chlorine. And I want to show chlorine in its hybridized form as well, which would be a 3 sp3. What now? Like having to name them or write their symbols or something? The only thing you're going to need to know about the periodic table is how to use it, how to recognize patterns.
Jeez, Raymond. Almost had a stroke.
Okay. Now imagine trying to draw all this so that it overlaps this orbital right here, and I need 4 of these chlorines. Imagine trying to draw out 4 chlorines so they overlap these 4 carbon atom orbitals. And that's a simple molecule. It can get really, really complex, especially when we get double and triple bonding. Just not possible to use orbital notation to show how this overlapping takes place. Okay, it gets just too complex. Well, that's where electron dot notation is so cool. Okay? What electron dot notation doesn't show you is the overlapping and sharing of electrons that actually occur inside an orbital. Okay? These orbitals are not two separate orbitals anymore. They're one. Okay? You ever been to a wedding? And a lot of times they say two become one in a wedding, right? Well, it's kind of like, well, there's two becoming one right there. Really is, okay? So with carbon, we have there, we need to figure out how many dots to put around chlorine in that electron dot formula. Well, in electron dot notation, how many dots do I put around a chlorine? Get your periodic table out and figure it out. How many dots do you put around chlorine in an electron dot formula? Hmm?
Is it 17?
No. Only the valence electrons go in the electron dot formulas. Not the whole set. Just the valence electrons go in an electron dot formula. How many? 7. 1 on each of the 4 sides. Pair up. Okay? 1 on each of the 4 sides and pair up. 1 on each of the 4 sides and pair up. Oop, 1 right here. Okay.
How many we got to make?
Well, there's 4 chlorines here, right? Okay, well, let me show you how we can use electron dots then to accomplish the same sort of thing if you really, but you've got to understand electron dots is simplified. Okay, we went from orbital notation to electron configurations. That simplified it, right? Then we went to electron dots, which is simplifying even more. You have to know that all this other stuff is going on, even though we're showing this super simplified version of it. You with me? Okay? So we can show that we can share those 2 electrons in an orbital just by circling them. Looky here. And so what happens then is, we started out with just electron dot formulas for carbon and 4 chlorines. We showed the sharing arrangement just by putting those circles around the electrons that are going to share. And from that, then, we're going to do what's called a Lewis dot formula, where we squeeze the electrons between the carbons and chlorines. Okay, so I'll squeeze them in there like that. If I squeeze them, they'll squish one to the side. Okay, I squeeze these together. Eventually, those 2 dots squeeze to the side. Squeeze these 2 together right here. They're going to the 2 electrons squeeze to the side. Does you see what I'm doing?
Yeah.
Now, I still have to show the other dots around the chlorines. Okay? And so you end up with what's called a Lewis dot formula. Y'all, you're supposed to turn off your phones in here during instruction or tests or quizzes. Phones have to be off and put away. Okay? So we started out with the electron dot formulas over here. So that was the electron dot formula. Then the whole thing became a sharing arrangement. And then from that, then we were able to come up with the Lewis dot formula. But this allows me to show that I'm sharing 2 electrons between each chlorine and the carbon, which I could have shown by doing a really, really complex structure with orbital notation, but that's become so cumbersome it's like not even worth trying to do after a while. And this was a simple molecule. If we did a more complex molecule, wow. Imagine trying to do that. Couldn't do it. Okay? Does that make sense? But now even this is simplified, because what's really happening is we're hybridizing orbitals. And we're putting, this would be like where the carbon goes And there would be a chlorine on each one of these ends instead of just the two hydrogens. You with me? A lot to keep up with, isn't it? Your head spinning? Okay. That's good. Because that means we're pushing those the cascading electrons through new neuron paths. We're crashing through the old ones and creating new neuron paths. That's good. Huh? So, what? You just want to, be in high school for the rest of your life?
Yes.
Nah.
Kick you out at 21.
Nah. Well, they would kick you out, and then what are you going to do? Okay. All right. Where? Right there?